Okay, so let's move to the first topic that we treat in detail, which is rainfall runoff modeling. And I mentioned to you that rainfall runoff modeling for us is instrumental to estimating water resources availability. And I mentioned that the first step, of course, first option that we can use to estimate water resources availability is data analysis. But I also reported that unfortunately hydrological data are not very often available, and in particular river flow data, because to measure river flows is not easy. It's an expensive activity, and also a continuous check of the measuring devices and the measuring techniques is needed. And therefore only in a few cross-river sections we can rely on river flow data. And in this case, the analysis is relatively easy, because basically in water resources management, what we need is an estimate of the average river flow, the mean river flow, averaged over a long period at a given time scale. So I mentioned monthly, for instance, river flows, monthly mean river flows. And if this is the estimate that you need and you have data, it's very easy, as you can understand, to compute the average of all the river flows that you observed in January, all the river flows that you observed in February, and so on. So the analysis, if you have data, is in principle straightforward. But unfortunately, as I mentioned, data are not frequently available, and therefore the second option that we have at disposal is rainfall runoff modeling, allowing us to convert rainfall measurements in river flow data. And the motivation for this idea is related to the increased availability of river flow data of rainfall data with respect to river flow data. Rainfall observations are more easily available in view of the fact that to measure rainfall is easier than measuring river flows. Nevertheless, I mentioned that even for rainfall, although we have a higher density of rain gauges with respect to river flow gauges, even though this above mentioned higher density, there is the problem that very often the length, the observation period of this rainfall data is not extended enough, because climate is varying, as we know. And therefore, this means that to get a reliable estimate of mean rainfall at a given time scale, you need a long series of data because of this variability of rainfall. Variability is much varying in space and time. Very often you experience in practice the variability of rainfall, especially during summer, during showers. There are very significant variation of rainfall intensity moving. While you drive, usually you see that suddenly you get into a storm, and then in equally rapid way you get out of it. This means that rainfall is spatially variable a lot, and also varying in time very significantly. And therefore, it follows that to get a good estimate of rainfall distribution in time and space, you will need very long records, which not always are available. But in any case, this increased availability of rainfall data with respect to river flow ones makes rainfall runoff modeling an attractive option. Rainfall runoff models are also used to predict flood flows, therefore deriving design variable for bridges, for levees. Levees are argil in Italian. And design variables for other kinds of hydraulic works, In this particular case, we are interested in rainfall runoff models for estimating water resources availability. This first slide is just a summary. It's just a summary of what hydrology is expected to provide for water resources management. We already discussed about this, and the lack of historical information, you see, again, makes estimation of water resources availability a relevant technical problem. This is again a sketch of the hydrological cycle. We already mentioned it, so I'm not spending more time. While here we have a flow chart of the hydrological cycle, which basically depict in a more useful way, if you have to prepare an algorithm, a flow chart of the processes, starting from precipitation, rainfall, to overland flow, infiltration, and I already mentioned to you that this separation, this classical separation between overland flow, surface runoff, and infiltration is somehow questioned today because it's not so clear if they are indeed separate flows. But in any case, this is a classical view which also highlights that infiltration contributes to groundwater recharge, and then groundwater flow, subsurface flow, and the combination of the two flows, the surface runoff and the subsurface flows, contributes to the runoff to the streams and oceans. Now, we basically know, we have an idea of these individual processes. Our task in the rainfall runoff transformation, strictly speaking, is to quantify all these processes through mathematical relationship. What we want is an analytical relationship that relates rainfall to runoff. Sorry. So we need this kind of analytical relationship, which traditionally takes the form of a deterministic relationship. Deterministic means that for one given input, you always get the same output. So there is a one-to-one relationship between input, including initial conditions, and including catchment behaviors, one single valued relationship between input and output. What I just said, the deterministic relationship, is actually questioned in modern hydrology because a deterministic relationship implies that there is no room for random variation. Again, a single input produces a single output. Why? Some researchers are convinced that there are random processes taking place in the hydrological cycle. I try to better explain what is a random process. It's a process where a decision, a selection between different options is taken randomly. Like, let's imagine a drop of water which rains in a given point of the topographical surface, of the Earth's surface. And then this drop, let's assume that flows on the surface, does not infiltrate. Of course, can in general follow different ways to go downstream. Let's think, for instance, to a drop that falls right on the divide between two watersheds, just on the divide. The difference between flowing downstream on the left of the divide or on the right of the divide can be thought of as a random process. The drop can either go on the left or on the right, and the distinction between the two options is done according to a random process. Like if you toss a coin. If you toss a coin, of course, the outcome, head or cross, is just a random process. And in many cases, even during the travel, during the trip that a drop follows to get downstream, there are some instances in where the difference between one option or the other is just taken accordingly to a random selection. And if you allowed randomness to be present in the hydrological cycle, at least in part, then it means that a deterministic relationship is not appropriate. But a statistical description would be more appropriate. Therefore, there are some discussion ongoing where people say, well, what's the best solution? I just submitted a paper for consideration in a scientific journal that is placed at the top of my webpage, where this problem is treated, and where a different methodology is proposed to take into account randomness in the hydrological cycle, which does not make a very big difference from a practical point of view, but from a methodological point of view, there is indeed some difference. But let's consider now that we rely on a deterministic relationship because it's easier. And as I said, from a practical point of view, there is not much difference. So let's rely on a deterministic relationship for now. And it's a challenging task to be able to write a deterministic relationship describing these processes. And of course, what we should ask ourselves when we wonder how to write this kind of deterministic relationship, we have to think about organizing principles, like theoretical principles that are followed by hydrological processes. Let me make an example. Conservation of mass is an organizing principle. So we have to wonder what are these principles that are valid in the hydrological cycle, in the rain-for-runoff transformation. Sorry. Okay, so in order to identify these principles, we should think about these phenomena. We should think of them. And to identify physical laws, or in general laws that can be applied, that can be applied to the hydrological cycle and written in mathematical form. And there is a very compelling evidence that we have to consider first of all. The compelling evidence is that hydrology basically describes water flows, describe displacement of water. Therefore, hydrology should call into play fluid mechanics. Fluid mechanics is the science that describes the movement of fluids. This is a very straightforward consideration, hydrology, fluid mechanics. And then, if we think about fluid mechanics, we should soon consider that conservation of mass and energy are satisfied in fluid mechanics, as well as Newton's laws that we will describe here by making reference to this itemized list. These are Newton laws. Every object in a state, first Newton law, of uniform motion tends to remain in that state of motion unless an external force is applied, which is the first Newton law. Second Newton law, we all know these laws, I'm just translating in English. The relationship between an object mass m, its acceleration a, and the applied force F is simply F equal m times a. Acceleration and force are vectors. And then the third Newton's law, for every action there is an equal and opposite reaction. What is very much relevant for us is conservation of mass and energy. Because indeed, the engine moving the hydrological cycle is energy, thermal energy that comes from the sun, and energy that is originated by gravity forces, meaning a conversion from position energy to kinematic energy. Therefore, for sure, we have to think about conservation of mass and energy in rainfall runoff modeling. How many of these laws do we need? How many organizing principles? It depends on the variables. Because if we think about rainfall runoff modeling, we are talking about a relationship between an input variable, which is known, that is rainfall, and an output variable, which is unknown, that is runoff, river flow. So at least we need one mathematical relationship. If the unknown variable is just one. But in many cases, if we increase model complexity, we need also to introduce state variables, like water storage. And this is an additional unknown. And therefore, we need to apply two conservation principles. And with the increasing number of state variables, we have to increase the number of, I call them constitutive equations, which come from the application of a conservation law. Conservation of mass, conservation of energy. We have at least two of them that are really available, and maybe more, because there are many different forms of conservation of energy that we can impose. So basically, we have to identify the basic principles, which are conservation of mass and energy, and the number of principles of conservation laws to be applied depends on the structure of the model. And the structure of the model in itself depends on the kind of problem you have to deal with. Sorry, just looking. Okay, so conservation laws, conservation of mass, is also called the continuity equation. Therefore, we can impose during the rainfall runoff transformation the conservation of the water volume, of the water mass. And for imposing conservation of energy, we can use the energy and momentum conservation equations, which differ because you know that depending on the type of process, in some cases you have conservation of energy, and in some cases you have conservation of momentum. Momentum is quantità di moto in Italian. And momentum is a vectorial variable, while energy is a scalar, as you know. And depending on the model structure, depending on the state variables that you introduce, depending on the need or not to model also water velocity, then you may choose between conservation of energy and conservation of momentum. And there is one problem here, that hydrological processes are typically heterogeneous, highly heterogeneous in space and time. Meaning that you have very significant changes in process structure and hydrological variables along time, as well as very significant changes in space. I already mentioned to you the high variability of rainfall in space and time, but not only rainfall is varying much. Let's think about spatial variability of soil, for instance, soil permeability. Sometimes you just move 1 meter apart and you find a different permeability. For instance, if you move from a street, from a paved road to the side of the road, you find a completely different environment. Which means that if the soil properties and then flow properties are very much varying in space. But think also about the slope of the ground, which of course is influential on the way a drop travels downstream. This is very much variable in space. And let's think about soil moisture. Even soil moisture is very much varying, depends on rainfall. When it rains, the soil is wet. When it doesn't rain, it's dry, with very significant variability. But also think about land cover. Land cover is very much varying in space and time. During winter, you have a different coverage of the Earth's surface, so you have different infiltration. There is a very significant heterogeneity and no stationarity. Usually when one says heterogeneity means variation, spatial variation. No stationarity means time variation. Even if no stationarity should be, strictly speaking, referred only to stochastic processes, not deterministic ones. But I think you understand the meaning. No stationarity, meaning that a process is changing its behavior in time. Now, this is a problem because indeed, this high spatial and temporal variability implies that if you want to draw a very detailed representation, you must be able to account for these changes. It means that, think about the time step. You can't use very huge time steps because with the huge time step, you neglect the sub-step variability. If you model river flow at monthly time scale, I just mentioned to you that you are ignoring the sub-monthly variability. You are ignoring the variability, the day-by-day variability. And if you model at large spatial scale, in the same way you neglect the fine scale variability, meaning that, for instance, if I want to model infiltration and I want to model it at the scale of 100 by 100 meters, which is a very detailed scale, by the way, but nevertheless it means that I am neglecting the variability that happens at the time scale, the spatial scale of 1 centimeter, which is relevant. So if I take a spatial scale of 100 by 100 meters, means that if I am centering over a road, I assume that the permeability of all this square cell is equal to the permeability that I measured on the center of gravity, which is the road. Means that I have an impervious area. I am assuming that the area is impervious, even well far from the road. So I'm making an approximation. And therefore uncertainty is introduced. And for this reason, some researchers proposed about after 1970 to use very detailed representation, spatial representation of watersheds. With watershed, I introduce a definition which is also called in English river basin or catchment, depending on the US and UK English language. Usually they are treated in the scientific literature as synonyms: watershed, catchment, or basin. And the translation in Italian is bacino idrografico. And the watershed, catchment, basin, is given by the topographical surface, is defined with reference to a cross-river section, first of all. So watershed, catchment, river basin is defined with reference to a cross-river section, and it's given by the topographical surface such that only the water, all and only the water raining on this surface flows across the given cross-river section. I'm repeating. Definition of catchment, river basin, watershed, for a given cross-river section. The definition is the topographical surface such that all and only the water that rains on this area contributes to the river flows at the given cross-river section. This implies that if you identify your cross-river section, which is here, which is perpendicular, as I told you, to the mean direction of the river flow, usually the river basin, the contributing area, is then identified by drawing a sketch like so, which includes, again, which means that if a drop rains here, for sure, this water we find passing through the cross-river section after a certain time. And second consequence, if a drop rains here, we don't find it through the cross-river section. Again, it's given the watershed by the topographical surface such that all the water and only the water that rained over that surface contributes to the runoff. Please remember this definition because it's very simple, but I see, and I don't know why, I don't know, maybe because it's a nasty definition, but I realize that for students it's difficult to remember this concept. While the concept of watershed is very much important for an hydrologist. It's one of the basic concepts. When you speak about a watershed, a bacino hydrographico, you must exactly know what are you talking about. You already took some courses on hydrology, and therefore you know that identifying this topographic surface is not easy. And usually you follow the divide, the watershed divide, topographical divide, which means that you assume that the topographical divide is equal to the phreatic divide, underground divide, which is not true because, in general it's not true because let's make a section. Here you have your river, and then you have the hill slope, and then you have the divide. Okay? So of course, it happens that if a drop rains here, then it goes to the river, that's fine. But let's assume that, and of course you know that if you assume that if a drop falls here, then it goes on the other side of the divide, and therefore you assume that it doesn't contribute to the runoff here. And I said if it drops right here, it's a random process probably, whether or not we find the drop in the river. Okay. But let's consider the case, which is very frequent in practice, where you have an impervious layer of rock, which is just displaced like this. What does this mean? It means that this drop that falls here goes, probably infiltrates, and then goes along here, and goes to the river. Why this? Because the phreatic divide is here. It's not coincident with the topographic divide. But given that to identify the phreatic divide, the underground divide, is very difficult because you need a perfect knowledge of the geology, then usually people take the assumption that the topographic divide is representative. Okay, then you identify the sketchment, and to go back to my original reasoning, a researcher proposed, starting from 1970, to subdivide the catchment into small subunits to be able to describe the variability of soil properties and hydrological processes within the catchment. This means that your equations, conservation laws, should be applied to the scale of each single grid cell. You get a grid composed by many cells, and you apply your conservation equation for each cell, meaning that the number of equations, of course, is exploding. But fortunately, and in fact I said this theory was promoted after 1970, fortunately now we have these amazing PCs And I can tell you that the computing capacity that now is given by even an old computer like this was unthinkable in the 90s. In 95, it was unthinkable to have such computing capacity at disposal. So now it's possible to let the number of equations explode and to make these detailed descriptions, even though you don't get a full description of the heterogeneity, because even if you decrease the size of these cells to some tens of meters, you can't go lower than that at present. You can't go to the scale of 1 centimeter, because otherwise really the number of equations is unmanageable. So even if you reduce to the scale of like 20 meters, you don't describe with full detail heterogeneity, because when we talk about heterogeneity of the soil properties, we talk about centimeters. And to give you an idea, for a basin, a watershed like the Secchia River Basin, which is about 1,000 square kilometers in extension, I made an experiment, and I adopted such kind of representation where I used square cells whose side was 250 meters. And even with a cell size of 250 meters, which one would say they are huge, I got 25,000 square cells to manage, with some like 5-6 equations per each cell. So you get more than 100,000 equations to manage. So it becomes tricky. So even in this case in which you adopt this detailed representation, you don't get a full description. But nevertheless, let's now go back to the concept, which is we identify the spatial scale of reference, and we apply to this spatial scale the conservation laws. I'm stopping here, but I am anticipating for next Monday that the basic equation is Reynolds theorem, which I've explained to you, from the Reynolds theorem, any conservation law can be derived: conservation of mass, conservation of energy. So we will describe in detail the Reynolds theorem, along with the definition of control volume, which means the volume to which the conservation laws are applied. Okay, for the next week we will meet on Monday, and take a note, on Tuesday, bring your PC, we will start making some calculation. And on Tuesday I'm planning to make a 1-hour lecture and then 2 hours of calculations. And I want just to check with you, please raise your hand who already started the program MATLAB at least once in his life. Nobody? I can't believe that. Okay, that's fine. 50%. Who never started it? Sorry, there is an inconsistency. Who never started it? So I guess that everybody already started at least once MATLAB. Okay. Okay. And the second question: do you know the program R, which is something similar to MATLAB? Raise your hand. Do you know it? Yes? Who? Yes? Nobody. Okay, fine. Therefore, I will introduce you to this programming language, which is similar to MATLAB, and I think has some nice features, and also I'm considering it for 2 reasons. First of all, because I am a fan, and this is the main reason. Second, I think that the knowledge of both packages really integrates very much well. And another last question, Octave. Do you know, somebody knows Octave? Yes? Just one? Okay. Octave is an open source emulation of MATLAB. I highly suggest you to try it, because MATLAB is commercial, guys. It's a bit of a problem. Okay, see you next week.